Let us do a variation in the particle in a box problem. We are now dealing with an electron which is confined in the ground state in a one-dimensional box of width 10 to the power minus 10 meter, which is the order of a size of an atom. This is angstrom. Its ground state energy is 38 electron volt. We need to calculate the energy for the electron is in its first excited state. This is problem 1. Second problem is we need to calculate the average force on the walls of the box when the electron is in its ground state, which means when the electron is in ground state, its energy is 38 electron volt. What is the amount of force the electron exerts on the walls of the box? For the first part of the problem, this is the familiar energy expression for particle in a box problem. For ground state, we have n equal to 1. If we put n equal to 1, this will be pi square h cross square by twice m a square. And first excited state energy will be 4 times the ground state energy. So the first excited state energy E2 turns out to be 152 electron volt. That is 4 multiplied with 38 electron volt. এবার আমরা পার্টিকেল ইন এ বক্স প্রবলেম যেটা করেছিলাম সেটাকে একটা ইলেকট্রনের জন্য দেখছি একটা প্র্যাকটিক্যাল সিনারিওতে। ইলেকট্রনটা একটা ওয়ান ডাইমেনশনাল বক্সের মধ্যে কনফাইন্ড হয়ে রয়েছে, আবদ্ধ হয়ে রয়েছে, বেরোতে পারছে না। বক্সের ডাইমেনশন 10 টু দি পাওয়ার মাইনাস 10 মিটার, অর্থাৎ অ্যাংস্ট্রম অর্ডারে। দুটো প্রবলেম আমাকে এখানে সলভ করতে হবে। একটা হচ্ছে ফার্স্ট এক্সাইটেড স্টেটে থাকা অবস্থায় ইলেকট্রনটার এনার্জি কত, আর সেকেন্ড প্রবলেমটা হচ্ছে গ্রাউন্ড স্টেটে থাকাকালীন ইলেকট্রনটা দেওয়ালে বক্সের দেওয়ালে যে পরিমাণ বল প্রয়োগ করবে তার অ্যাভারেজ ভ্যালু, তার গড় মান নির্ণয় করা। Now we know that this is the expression for the average force F equal to minus del A of the Hamiltonian H. This A is the dimension. And we have the equation of a stationary states, this one. This is our familiar Schrödinger equation, time independent Schrödinger equation. If we differentiate this equation, we will get this, because first we need to differentiate these terms, psi n constant, then we need to keep this energy term constant, and we need to differentiate the psi n wave function. This is equation 3. So if we multiply with the psi n star, that is generally we consider the wave functions as complex quantities. So if we multiply this equation with the psi n star, we get equation number 4. Please take care of the minus sign here. I have switched the terms. Here I have minus del A of En. Here we have plus del A of En, because we have made a side change. Now if we integrate the left hand side, we get equation number 5, and now equation number 5 will give me basically the expectation value of the Hamiltonian in this complex states. Now as H is a real quantity, this Hamiltonian is a real quantity, this thing is equal to 0. So the left hand side is equal to 0 and the right hand side is equal to 0. So as the right hand side is equal to 0, we have this, because psi n star del A of Hamiltonian psi n is basically the expectation value of del A of the Hamiltonian in the state psi n. So this is del A of the Hamiltonian, and the expectation value left hand side we have del A of En, because this is a scalar quantity. So this will come out, and psi n star psi n is equal to 1 because of the normalization condition. Then from equation 1 we have a force expression here. So we have from equation 1 the force is equal to minus del A of En. So we need to differentiate the energy expression with respect to A. So I have differentiated the energy expression with respect to A, and we have got force equal to 2 by A E1. And if we replace the value, substitute the value of E1 as 38 electron volt, I will get this expression. Because this 10 to the power minus 10 is in centimeter, this is in electron volt. So this is 7.6 into 10 to the power 10 electron volt per centimeter. You can obtain this in dyne.